SPARCS has reached first light. That is the first practical proof that the telescope, detectors, and readout chain are working in orbit. NASA released a pair of images recorded on February 6, 2026, about 3 weeks after launch on a SpaceX Falcon 9 on Jan 11th. The images show the same star field into bands at the same time, near ultraviolet on the left and far ultraviolet on the right. That matters now, because first light is the point where a mission stops being mostly a hardware story and starts becoming a data story. For viewers, the key takeaway is simple. SPARCS is not just alive in orbit. It is already doing the exact kind of simultaneous ultraviolet observing it was built to do. That makes this a meaningful operations milestone, not just a ceremonial one. The image pair is useful because the difference between the two panels carries information. In NASA's description, one star appears in the far UV, while multiple stars appear in the near UV. In plain terms, that suggests the star, seen in both channels, is the hottest one in that view. So the image is doing more than showing a nice technical success. It is demonstrating the value of simultaneous double ultraviolet data. SPARCS is set up to compare how stars behave across near UV and far UV without needing separate missions or on matching observation windows. That is important because stars are variable. If you measure one band on one day and another later, you can miss the real timing and strength of activity. This first pair is a simple but concrete proof that SPARCS can separate those signals in the way the mission needs. SPARCS is focused on low-mass stars, around 30% to 50% of the sun's mass. That is a very deliberate target choice. These stars are common in the Milky Way, and NASA notes they host the majority of the galaxy's roughly 50 billion habitable on terrestrial planets. But there is a catch. A planet can sit in the temperature range where liquid water is possible and still face a rough radiation environment if its star flares often or emits strong ultraviolet bursts. That is where SPARCS fits. The mission will monitor flares and sunspot activity, aiming at about 20 low-mass stars over a 1-year mission, with observing runs lasting from 5 to 45 days. So the viewer payoff here is not abstract. SPARCS helps connect stellar activity to the real question people care about: whether planets around common stars are exposed to conditions that help or hurt habitability. The deeper story is in the instrument design. NASA's SPARCS is the first spacecraft dedicated to continuously and simultaneously monitoring far-ultraviolet and near-ultraviolet radiation from low-mass stars. That is the mission-level distinction. At the hardware level, the camera system uses detector-integrated filters deposited directly onto specially developed UV-sensitive delta-to detectors. That removes the need for a separate filter element. In practical terms, fewer layers can mean better sensitivity and a cleaner optical path. NASA describes the result as among the most sensitive systems of its kind ever flown in space. The filters, detectors, and electronics came from the micro devices laboratory at JPL. So if you are tracking what changed, this is the answer. SPARCS is not just a small telescope in orbit. It is a compact test of how more capable ultraviolet sensing can be packaged into a low-cost CubeSat mission. The right red on first light is measured, not dramatic. What matters is that SPARCS has cleared an early operational hurdle and shown simultaneous near UV and far UV imaging in orbit. What does not matter yet is any broad claim about exoplanet habitability or a full scientific result from one image pair. Those conclusions need repeated monitoring over days to weeks, which is exactly how the mission is designed to operate. The real test now is consistency. Can SPARCS deliver stable, sensitive observations across its planned targets and capture flare behavior over time? If it can, the mission becomes useful in two ways at once. It adds new data on how low-mass stars behave, and it strengthens the case that CubeSats can do serious focused astrophysics when the instrument design is tight. That is the signal here. The noise is reading too much into first light alone.